so now let's talk about making your own machine learning, not using these public ones that are big and powerful, but they're controlled by someone else, and also any information you send them is being exposed publicly. So let's start making our own with Tensorflow. So down here at ML100 is the stuff, and this, by the way, is what I got out of these textbooks. I started with these textbooks here, and these textbooks show you how to make your own machine learning with Tensorflow, and I didn't move into the large language models until later. So I'm going to clear some of these other windows. All right. So what you do is you just make it in Colab. So I thought, again, this is wonderful for teachers because students don't have to have a powerful computer or Linux or anything. They can just use this in a browser, and it turns out to be extremely powerful, powerful enough to run machine learning for free, a lot better than I expected. And you don't need much code at all to do it. The Python libraries are so friendly that it's only like a small number of lines of code to do anything. So you run import Tensorflow. Tensorflow is the main library we're going to use that does the mathematics required for machine learning. So this just shows that the Tensorflow library is available in the Google Colab environment, and it is. It has some version of it available. So now this is where you get the essence of machine learning. And I used to be a research scientist long ago, and this is the fundamental thing a research scientist does, right? You measure, an experimentalist, you measure something. You get some pattern, and then you fit a curve through it. So here you have some x and y. So here's a x going up by 1 and y going up by 2. And they say, what's the relationship here? And you can see that x goes from 0 to 1 to 2, and y goes from -1 to 1 to 3. So it looks like every time x goes up by 1, y goes up by 2. And when x is 0, y is -1. So the mathematical relationship is y equals 2x minus 1. And this process of going from specific data and finding the pattern is what machine learning does. And that used to take a human to do this. And then if you want to put it in a computer, you would just put in this equation in the computer. And the point is, machine learning will deduce the pattern from just the data by learning. And here's all the code it takes to do that. About 10 lines of code. So throw that in your Colab, and you can either put it on top of the old code here. It will remember the results from the old code, or you can make a new block of code here and put it below, either way. And so when you run this, here's the data coming in, -1, here's the x and the y coming in. X is an array and y is an array. And here it's just going to make a model with one neuron. So this has just got one processing neuron that's linear. It's going to use gradient descent. I forget what the S is, stochastic gradient descent. So that means it's going to guess values of the parameters, and then it's just going to move them in a way that causes the error to go down. And it's going to do that 500 times. So here are the results coming in below. And if I get up to the earlier parts of it, so when it started, the loss, which is the measure of how badly it fits those points, was 3. But as you can see, every step it comes down. Down, down, down. And it gets down to a very small value, like 10 to the -5. And when it's done, to see if it worked, I print out 18.9. In the code, to test it, I predicted what the answer should be for 20. Predict 10, what the answer should be for 10. And the pattern is y is 2x minus 1, so the right answer for 10 is 19. And it did get very close. It got 18.99 or 18.95. Let me get back to the bottom. Okay, 18.98. So it did learn quite well how to fit this simple linear model. Now this is a single neuron that simply does a linear mathematical calculation. So all it's doing is finding these values, the slope and intercept, 2 and -1. You can also output the data to see what it learned. Here's another version of it that will print out the parameters it learned. So I'm going to go up here, get rid of the old code and put in the new code. This is just going to print out the parameters in addition to the prediction. All right. See, now it's gotten down to a ridiculously small error, and so now the prediction for the value of 10 is 19, very close, and the parameters it found were minus 0.98 and 1.99, so that's very close to 2, and that's very close to minus 1. So it's doing very well. It's getting within 1% of the right value for the parameters, as you would expect. So now, let's try giving it some errors. I just added some random noise to y to make the problem a little harder. So let's go back to the code, and I'll just comment out the old y and put in the new y, which is just, I added some random little numbers to it to make it have a little bit of noise, and see if it can fit through that. And so it's doing 500 steps, and as you can see, they go very fast. And here's what it learned. Again, minus 0.99 and 1.99. Again, it did a fine job. Even with noise, it's zeroed in on the right parameters very closely. Now, if we try to fit something that is not a straight line, this is actually a parabola, x squared minus 4x minus 5. So putting a straight line through this with one neuron doing a linear calculation, it's not going to be possible to do a very good fit. So let's put that in. We'll try fitting that one. All right.
Sam, with this specification of neuron count, is it the kind of the strategy here that for every additional neuron you're able to compute a different dimension simultaneously?
Yes, absolutely. And that is, by the way, how you rate machine learning models, by how many parameters they have, which is how many connections between neurons they have. And so here I have only 2 parameters, and the Tensorflow, the ChatGPT and the Google Bard we're using, those have 1 trillion parameters. So, a big step up. And so here, see, it wasn't able to get the loss very small at all. The loss stayed up at 4, which is really bad. And now let's try a complex curve. This is going to be x sine x, so it's curvy. You see that here. This is now 0.1x times cosine of x, and then plus some random noise. And it's going to plot out the results, so we can see how good the fit is. So I'm going to clear this old stuff and just put it up here. Okay. All right, so it's... Now notice here, you can see the structure of the model. There is one input neuron to take the input value of x. There is one output neuron to be the value of y. But instead of just one neuron to do the processing, it has 2 hidden layers of 64 neurons in the middle. So it can learn a much more complicated situation. And it gives you the parameters at the start here. I scroll in there. Here it tells you a description of your model. So the model is one input, 64 hidden neurons in a hidden layer, another 64 neurons, and one output layer. So now the total parameters is 4,355. So this is a much more complicated model. And here it is running. Still runs really fast, even in this nice free environment, whatever amount of processing they're giving me. So here's 100 cycles of learning. And as you can see, it did a good job of finding the curve through that noisy data. And there have been some flags to find here and there as you go through. And then you can try using fewer layers. So maybe you wonder if you really need 2 layers of 64 neurons to do that. So you can go up here and just comment out one of these hidden lines. They call them hidden neurons because they aren't connected directly to the input or the output. They're the internal processing. So, nope, it's not letting me click. Click, I say. There we are. There we go. Now I've commented out one of the 64s, so it has 1 layer of hidden neurons. And let's see how much that degrades the output. Now the previous one had 4,000 parameters, and this is going to have a lot less. Now it has, got to quit scrolling off the screen. Now it has only 195 parameters instead of 4,000. So you expect it to be much worse. And it is much worse. It's just a very crude fit of just sort of line segments through the data. So there's flags to find here. I had variant ones to try. Try 32 units, 1 layer, 16, 2 layers, 4 units, 3, 4 units, 4, and see which one is best. You have to try them a few times too because there's noise. And then there's one where you can vary the amount of input data and the amount of noise. I don't know why you need 1,000 points of input data. It seemed to me like 100 points should be enough to trace that out. But in fact, I found that when you cut down the number of points, the quality goes way down. So anyway, there's various versions of this to try. And there's that one. I'm going to stop this recording.